Good morning, everyone. My name is Yasser. Me and my team has presented a presentation on smart cities, clean mobility, the future of public transport, and EV charging. Before we dive further, let's quickly go through table of content. At first, we have executive summary followed by a quick introduction. Then we will have approaches and methods. Then we'll follow through findings, and then lastly but not least, we'll have appendix. As DEV company advances its sustainable goals, replacing diesel buses with 1,300 electrical buses and building 1,028 bus stops, it will cut emissions, reduce cost, and boost public transports up to 40% by 2030. This shift will bring low carbon dioxide, removing fossil fuels buses from roads, cost savings, which will include higher upfront costs but reduces long term OPEX and maintenance, and it will have better access, meaning more routes in underserved areas to improve mobility. To meet the rising EV demand, the company plans to raise parking for low emission vehicles from 5% to 15% by 2050. Instead of full grid reliance, solar powered chargers will cut energy costs and erase grid overload. This includes smart charging, which will use less grid use and more EV ready spots, scalable growth, which will fix the design to match the future needs, low cost and emissions, solar cuts power bills and carbon dioxide. Through these steps, the company leads to shift to a cleaner and smarter urban future.
Building a low-carbon mobility future for DevCo. As DevCo prepares for future growth, the city is prioritizing clean, efficient, and inclusive mobility systems that align with long-term climate goals. Transportation remains a major contributor to urban emissions and energy use, which makes transforming this sector essential to DevCo's sustainable development strategy. The focus of this project is on two core mobility initiatives that support DevCo's ambition to become a smart, low-emission city by 2050. Electrification of public transport, replacing 1,399 diesel buses with electric buses and constructing 1,028 modern accessible bus stops to increase network efficiency, reduce pollution, and improve service across all city zones. EV charging infrastructure development, expanding charging capacity while reducing reliance on fully grid-connected systems by integrating solar-powered and hybrid charging solutions to manage energy demand and support the growing EV population. This project evaluates this initiative from both a financial and environmental perspective, helping identify high-impact investments that deliver long-term benefits in carbon reduction, cost savings, and mobility. The shift to sustainable mobility. DevCo's current transport system heavily depends on diesel buses and private vehicles, leading to high emission and congestion. EV charging infrastructure is minimal and mostly reliant on grid electricity. Public transport accessibility is limited in several city zones, discouraging widespread adoption. Complication. Diesel buses contribute to rising CO2 emissions, poor air quality, and volatile operation costs due to fuel price fluctuations. Grid-dependent EV charging creates pressure on the energy networks and limits scalability. Without infrastructure upgrades, EV growth and public transport use will stagnate, undermining the city's 2050 net zero targets. Resolution. Electrify public transport by deploying 1,399 e-buses and 1,028 new buses stops to increase reliability, access, and sustainability. Develop a smart EV charging network with lower grid dependency by incorporating solar-powered systems and better parking provisions. Use financial and carbon modeling to identify cost-effective, high-impact solutions that align with DevCo's clean city vision. A data-driven path towards sustainability, urban mobility. Through the electrification and public transport and the development of solar-integrated EV charging infrastructure, DevCo is building a cleaner, smarter, and more resilient urban future. This project compares traditional diesel-based transport system and fully grid-dependent EV charging models against low-emission alternatives, using net present value and marginal abandonment cost analysis to evaluate both financial viability and environmental impact. By applying data-driven insights and long-term scenario planning, we demonstrate the sustainable mobility in DevCo is not only possible, it is economically and operationally strategic.
Now let's talk about the initiative approach. To access low carbon mobility plan, we compared the diesel-based businesses with two initiatives, the electrifying public transport and integrating solar into electrical charging. The model targets 40% mode share by 2030 with 1,300 electrical buses and 1,028 bus stops. We estimate that capex and opex with 2% CPI adjustments and calculated emission using energy and grid factor of 0.000568 kilowatt hour.
Step 1 was road network and bus stops. So we assume that 20% of DevCo's land is dedicated to roads totaling around 4.1 meters squared. With an average road width of 10 meters, this gives us approximately 411 kilometers of roads. Assuming a bus stop every 400 meters, we calculated 1,028 bus stops needed for the network, applicable to both diesel and electric buses. Step 2 was the type of bus stops. Bus stops are split into two categories: 68% mid-tier with 700 bus stops with basic shelters, and 32% premium 328 stops featuring air conditioning and enhanced amenities designed based on passenger traffic patterns. Based on these, each bus will take approximately 34 trips per day. This information was taken based on buses operating in Riyadh, Saudi Arabia. Step 3 considers the number of trips. So buses operate for 18 hours daily with a 1 hour break included, and each trip will take approximately 30 minutes, which leads to roughly 34 trips per bus per day. And this estimate aligns with operational data from comparable cities and considers realistic turnaround times. Step 4 considers the number of buses. So, to achieve a 40% public transport mode share, a fleet of 1399 electric buses is planned, which matches the current diesel fleet size. The fleet size supports the required frequency and passenger demand across the city routes. Step 5 is the bus model selected. So, electrical buses selected have a capacity of around 80 passengers with a range of 250 kilometers per full charge. Diesel buses equivalents hold similar capacity, but they have higher emissions and fuel costs. The choice balances operational efficiency and environmental benefits. Step 6 is the daily energy demand. Each electric bus consumes an average of 240 kilowatts per day based on the routine length and the typical driving patterns. For 1,399 buses, total daily electricity demand is estimated at 335,760 kilowatts, which guides charging infrastructure and capacity planning. Step number 7 considers the type of chargers. For fast chargers with a capacity of 150 kilowatts are chosen to enable quick turnaround during layovers. Chargers are distributed at bus depots and strategic locations to optimize charging schedules and maintain service reliability. Step number 8 considers the number of depots and chargers. 3 main bus depots are planned, each equipped with approximately 150 chargers, totaling 450 chargers citywide. Depot locations are optimized for efficient fleet operation and maintenance. Step number 9 is the number of fueling depots. For the diesel fleet, 5 fueling depots currently operate, handling daily refueling and maintenance. These will be phased out as the electric bus fleet scales up. Step 10 considers the carbon dioxide emissions of the initiative. Electric buses' annual carbon dioxide emissions are calculated by multiplying total electricity consumption by the grid carbon factor. This yields approximately 60,000 T carbon dioxide per year, which is significantly lower than the diesel emissions. Step 11 considers the carbon dioxide emissions of BAU. Diesel buses consume approximately 30 million liters of diesel annually, emitting 2.68 kg of carbon dioxide per liter, which results in 80,400 T's carbon dioxide per year, and this represents the baseline emissions to be reduced. Step 12 considers the capex of the initiative. Capex for electric buses, charging stations, depot upgrades, and bus stop modernization totals up to $1.2 billion. This includes higher upfront costs for vehicles and infrastructure compared to diesel. Step 13 considers the capex of BAU. Capital costs for diesel buses and existing infrastructure total approximately $700 million, which reflects lower vehicle costs but higher long-term OPEXs. Step 14 considers the OPEX of the initiative. Annual operating costs for electric buses, including maintenance, electricity, and labor, are estimated at $60 million, benefiting from lower energy and maintenance costs. And lastly, Step 15 considers the OPEX of BAU. Diesel bus operations incur higher yearly costs, approximately $85 million, due to fuel expenses, more frequent maintenance, and emissions compliance. Now I'm going to talk about the high-level methodology for EV. Step 1 is to focus on parking demand and growth assumption. current EV/hybrid parking provision is 5% of total city parking. Our initiative aims to raise this to 15% by 2050. Based on future projections of 100,000 total parking spaces, we can scale up from 5,000 EV-enabled spots to 15,000 by 2050. Step 2 considers charger type and tech split. We propose replacing 100% grid-connected chargers with a mixed system, 60% hybrid chargers, solar plus grid, 25% solar-powered standalone chargers, 15% fast DC chargers for high-demand areas. This mix balances cost, energy efficiency, and load on the grid. Step 3 considers energy demand estimation. Each EV is assumed to consume 15 kilowatts per day. With an estimated 15,000 EVs by 2050, the daily demand will equal to 225,000 kilowatts per day. Step number 4 considers the number of chargers required. Assuming that charger to vehicle ratio is 1:3, we need 5,000 chargers by 2050, where there are 3,000 hybrid solar grid chargers, 1250 solar only chargers, and 750 fast DC chargers. Charger locations will be spread across residential hubs, workspaces, and transport corridors. Step 5 considers carbon dioxide emissions, the initiative versus the BAU. As for the BAU, the grid only, it is around 127.8 T carbon dioxide per day, while it is 46,647 T carbon dioxide per year. For the initiative, which is solar integrated, we assume 50% solar supply, which comes down to 23,324 T carbon dioxide per year, 63.9 T carbon dioxide per day, and the carbon dioxide abated comes down to 23,323 T carbon dioxide per year. Step 6 considers the capex comparison, where the initiative capex for 2025 to 2050 is on an average of $45 million, which consists of an additional $10 million cost for solar infrastructure, whereas the BAU capex is where the grid-only chargers are around $25 million. Step 7 considers the OPEX comparison, where the initiatives is around $1.8 million per year, and the BAU's annual OPEX is around $3.5 million per year, with higher electricity costs and grid usage. Savings scale up over a 25-year project life, and a CPI of 2% is applied annually. Step 8 considers the NPV analysis using a 5% WACC. We calculated NPV by comparing the discounted cash flows of BAU versus the initiative over 25 years, again, which was 2025 to 2050, and we applied a 2% CPI annually. The NPV savings came up to $36 million. Step 9 considers the total carbon dioxide abatement over the 25 years. The total carbon dioxide abated was 583,075 T carbon dioxide, whereas the annual carbon dioxide abatement was around 23,323. Now, step 10 considers the marginal abatement cost, which is the MAC. We calculated the MAC to evaluate the cost effectiveness per ton of carbon dioxide reduced, which came down to $61.72 per T carbon dioxide. This is a strongly positive economic signal, which shows that each ton of carbon dioxide reduced brings over $60 in financial benefit when switching from grid-only to solar-integrated EV infrastructure.